There we go. We're recording now. Okay, just a suggestion. If you see it, I'm not recording, and it sounds like I'm saying something important. Not that I say important things too often, but if I do, just remind me to turn on the recording. Okay, let me go into the exam here, and I'm going to open this up. Okay. So at any rate, the first example was something that we really started the whole semester with, which is identifying what kind of variables we were working with. That's more important than it would appear because the variables are really, the variable types are really determine what kind of statistical tests you're going to do with them, how you're going to analyze that data. So I don't think everybody seemed to do pretty well on this. The only thing is that there's only one ordinal piece of ordinal data in here. That's the pain scale, I believe. Was there anything else that was ordinal? Nope. Right. Everything else was either nominal or numerical. And you would fill in the types there and so on and so forth. Now, as far as this histogram is concerned, it asks you things like, for instance, how many patients stayed at the center for 10 days or more. The height of these represents a frequency, right? It's categorical data, represents the number of people that stayed for that number of days. And so the length of stay is a numerical variable. So let's see, 10 days was 4 people and 2 people for 11 and 5. We would add those up and put it over 30. I believe the total number of people, if you add up these columns, was 30 days. So basically a third, of the people stayed for 10 days or more. What's the probability of staying at center for fewer than 8 days, not including 8 days? That would be 765. So it would be these, which would be 4, 5, 10 over, that was 33%. 10 or more was more, right? 4, 6, 11, 13, 14 out of 30 days. Okay, so that's basically what we would do with that. Trust me, if I didn't get the numbers right here, I'm going very quickly, but you get the idea how we got that. Oh, question 16, I'll definitely get to that. Okay, given patient stayed for, now this, the only twist here was we gave it a conditional element. Given that a patient stayed at the center for 11 days or more, given that we're only dealing with patients that stayed 11 days or more, what's the probability that patient stayed for 14 days? Well, only one patient stayed for 14 days out of the 2, 7, 9, 10, one out of the 10 that satisfied that first condition actually stayed for 14 days. So it's 1/10. There was another one that I was going to put in there that, the test was getting a little long, so I didn't put it in there. It was one of those tables that we gave you. Remember that one with the marital status and male or female, where that you could also play around with the probabilities as well. It was kind of a crosstab table, whereas rows were male or female, and the columns were like marital status, divorced, widowed, and so on and so forth. So I didn't bother putting one of those in there because we were already getting a little long in the number of examples. Okay, now here's a simple diagnostic test. Consider results of evaluation of a diagnostic test on a random sample from a population. So this population has been randomly sampled. It turns out that out of 1,000 people that we sampled, 100 have the disease. So the prevalence in the population is going to be 10%. 100. This is the total number of people that have the disease, whether they tested positive or negative. These are everybody in this column has the disease, and it's 100 people out of 1,000 people total that were sampled. What's the sensitivity of the test? Well, that's basically how well we can predict when a person who has the disease really does. And we see that we were successful 90 times out of 100. So the sensitivity of the test is 90%. The specificity, positive predictive value. I was going to say specificity. I guess I didn't ask it at this point. The positive predictive value it basically is asking, well, if you get a positive outcome, a positive diagnosis on this test, what's the probability you really have the disease? So let's see, we have 90 people that had the disease that tested positive. We have 198 that tested positive that did not have the disease, right? The specificity of this test was apparently about, I think it's about 80% or something like that. Is that what it is? Right? So 198 out of 900 people who didn't have the disease tested positive, right? So we wound up with more people testing positive who didn't have the disease than did have the disease. So a total of 288 people tested positive. So the positive predictive value is 90 over 288. The number of people that tested positive that really had the disease over 288, the total number of people that tested positive. That is a conditional probability, right? Because what are we saying there? We're saying the positive predictive value. What's the probability that you have the disease given that you have tested positive, right? Probability of disease plus that pipe symbol, given that you have tested positive, which is this right here. Okay, so T plus. Okay, what's the positive predictive value of this test? Then we just figured that out. Okay, at least we figured out the fraction anyway. Okay, and then we also we had an opportunity to apply the Bayes theorem using that formula, which is really, I think I put an explanation of this on. Did I put something on discussions board on this? It might have been the other course that I did that. I can post something to the discussions board. Basically, in this case, what we're going to do is we have a diagnostic test that's 99% accurate. The sensitivity is 99% on individuals with cancer. The specificity of it is 90%. 90% accurate for people without cancer, saying that they would test negative 90% of the time. Okay, and it produces, let's see, then the test is applied to a population with a very low prevalence of cancer, 1%, let's say. Okay, that's not very low, but it's low. If an individual receives a positive test, what's the probability to test the patient has cancer? In other words, positive predictive value. So we could actually apply that formula that we had, right? Maybe I can find that formula. You want to know something? It's probably easier for me to Google it than to find it on my computer. Let's see if I can't find it here. Calculation, let's see, images. Here we go. If I can't get this to come up here. Oh, it's tiny. It's tiny. Let me drag it off here and then blow it up. See if it's still readable if I blow it up. I think we can get away with that, I think. Okay. Now, let's take a look at this. The positive predictive value was before the total number of people that test positive that actually have the disease, in other words, the true positives, was on top, and the total number of positives was on the bottom. So the sensitivity, which is 99%, times the prevalence is going to be the percentage of people in the population that tested positive that have the disease. I'll give you a simpler example. Say 90%, let's say the prevalence is 10%. And let's say the sensitivity is 90%, right? 10% of the people have the disease. 90%, the test is 90% accurate. 0.90 times 0.10 comes out to 9%. Because 10% have the disease, but we're only 90% good at catching them. So 9% of the people in the population would test positive. So that's my true positive, my proportion of the population that's true positives. So these are the proportion percentage of people that are true positives. Well, then on the bottom, I want all the positives, the true positives and the false positives. So all I do is repeat that same formula here to get the true positives, and then I need to get the false positives. Well, how do I get the false positives? Well, first of all, I need to know how many people don't have the disease, and that's 1 minus the prevalence. So if I had said the prevalence was 10%, now I'm looking at 90% of the population who doesn't have the disease, right? So now the specificity is the percentage that you would be at getting that right. So that the specificity times 1 minus the prevalence would be what percentage of the population you would get true negatives for. right? That you would get that right. We don't want that. We want to know how much we got it wrong. So we would get it 1 minus the specificity. So if the specificity is 90%, 1 minus the specificity is 10%, means we would get it wrong 10% of the time. So the percentage of times we would get it wrong times the percentage of people that didn't have the disease would give us the number of false positives, the percentage of times we would get it wrong. So this is the true positives. We're adding the false positives. So the bottom has all the positives, like our 288 before, and the top has our true positives, whatever that was before. I don't even remember. Right? We could actually then do that. Now you could go online and check your work. Right? In the future, when you really have to do this for some reason. Suppose you're in a situation that you can't avoid and you actually have to use statistics for something, right? Now, God forbid that should occur to, at some point in the future. Well, what you could do is we could just go up here and say positive predictive value calculator. Okay, and let's see, I must have used this before because it looks like it's coming up here. Let's see what that one is. Oh, what do you know? Okay, what I said prevalence was here, 0.99. I'm sorry, 0.01. 0.01. And what was the sensitivity? 0.99. And what was the specificity of the actual problem? You remember? Was it that? I think that was on the previous example. Let me see if I can't get this out of the way. Why isn't it let me grab that? Oh, I know why, because there's a window open there. Okay. So let's see, what was it? Prevalence, 90%. It's 90% specificity. So it's going to be 0.9. Okay, make that go away, 0.9. So if you'd gone through that actual calculation, you would find that the positive predictive value is going to be, here it is, positive, it's going to be about 9%, right? About 10% or something like that. So 90% of people, 91% of people that take this test get a positive result are not actually going to have that disease. Even though the specificity and the sensitivity seems so good, the fact that it was a rare, the prevalence was low, means there's a lot of people you're testing that don't have the disease. Okay, and I haven't forgotten about that question. 16, we're getting there. Okay, according to behavioral risk data, 58% of Americans adhere to a sedentary lifestyle, assuming that surveillance guide. What is the probability of finding 8 or more individuals who are sedentary from a random sample of 10? Okay, well, that's a binomial distribution, right? So our number of successes, I'm only going to do this one in Excel. Okay, let's make that go away, and let's make this 200%. And let's make this more. Equal binom dist. Binom dist. There it goes. Okay, number of successes was, well, let's see the question here. The question was, according to the assuming what is the probability of finding 8 or more individuals? Now, we know this only works going down. So in order to find the probability of 8 or more, I have to subtract the probability of 7 or less from this. So my number of successes I'm interested in is 7, comma, my number of trials is 10 random samples. Probability is 0.58, comma, and true is going to give me my total probability of 6, 7, 5, 4, and so on and so forth. And that's going to be 86%. So it's going to leave about 14% chance that we would find a sample of 10 that's 58% of the sample of 10 that has 8 people in that sample of 10 that are sedentary. Okay, female athletes. I'm not going to bother open up. I think you've already gotten done this for a simple situation where you can use SPSS or Excel to find basic descriptive statistics. The only thing that might be a little bit tricky for you is when I ask you to factor this into 2 groups. Okay, let me just see if I can't find that file. high school student athletes, .sav. I'm going to pull up the, I am going to go for this one, which is the, let me find an open space here where I could drop it. Okay, like SPSS. Okay, come on, open up. Good. All right, good. Don't want that. I'm going to say open, data. I hope it imported. I hope I got it to the desktop there. SAV doesn't look like it was successful. Let me try that again. Yeah, I got so much stuff over here, it's hard for me to find the desktop, let alone save something to it. Let me close that. I don't need that. It's still there? Yeah. Okay, that should work now. And do I see it there? Not yet. Maybe we got to reload it. There it is now. Okay, let's open this up. And if I want the basic descriptive statistics for the BMIs of all these student athletes, I would go in here to analyze descriptive statistics. If it were a categorical variable, if I wanted to know, is a categorical variable here? If I wanted to know, I don't see one right off the bat. If there were a categorical variable like, for instance, were they obese or not obese, and it was a 1 or a 2 or something like that, I could use frequencies, analyze descriptive statistics, frequencies for categorical variables. If they, for instance, if they were U.S. citizens, for instance, that's a categorical variable. I could go into frequencies that would count them and just give me feedback on that count or percentages. If I want descriptive statistics for a numerical variable like BMI, I could go in here, move BMI into this column, and actually calculate various statistics for that mean of the BMI. Mean is 21, the maximum, minimum, and so on and so forth. If I wanted more information, I could go into Descriptive Statistics Explore, do the same thing, and wind up with more detailed statistics for the entire group, for all of these student athletes, same number, right? But just more information. Okay, the interquartile range, standard deviation now, and so on. More of the information is available to us about the distribution of these BMIs for these athletes. But now, let's say I wanted to define this a little bit further. Now, you know, this is an early version of the data here. I had transformed it for the version I gave you into sport. There was 1 and 2. And 1 and 2 was an aerobic or non-aerobic sport. That was our categorical variable. If I wanted to divide this up into 2 groups, I would have said analyze, descriptive statistics, explore, and I would move BMI into the dependence list, and then I would have moved the sport into the factor list. Okay, and it would have broken this up into many different categories, dividing the girls into the 2 categories, aerobic sports and non-aerobic sports, and doing the means and standard deviations and so on and so forth, all the stuff that Explore does, but having done it separately for girls in group 1 and girls in group 2. You could also go into plots and ask it to do a histogram and some other plots and so on and so forth. And again, they would do it for these individual groups. So now the first one we did was for the whole group. It did a box plot for us. This is all the girls. That's the that's the lowest BMI. That's the highest BMI. This is the median BMI. So we can see it's skewed, right? There's a few BMIs that are higher, right? And here we have there's actually that number of different groups. That's why the version I gave you only had 2 groups, right? And this was means and standard deviations for all of these groups. You would have only gotten 2 on the version I gave you. And these histograms really don't make much sense. Here's box plots for all the different sports activities and so on and so forth. It was much more interesting. We only did 1 or 2. So at any rate, that's how you would do that. I'm not going to open up that other data file because you do basically the same thing. Okay, next. I'm getting closer to 16 now. That's the one question somebody had, and here I am going through all this other stuff. But I just want to make sure that we have this. Everybody's got a pretty good handle on this. Okay, 15, 16. The heights of 10-year-olds, regardless of gender, closely follow a normal distribution with a mean of 55 inches and a standard deviation of 6 inches. Use this distribution for the following questions about height. Okay, and that is the height of 10-year-olds, not a sample. We didn't say that we sampled 10 or 50 or 100. This is just 10-year-olds in general. So it's a population we're dealing with here. What's the probability that a randomly chosen 10-year-old is shorter than 48 inches? Well, like I've suggested to you before, you should consider sketching this stuff out. Let me connect my tablet here so I can write. And this problem and the ones that follow it are really the real reason I wanted to go over this, because these normal distribution problems and these Z-table problems are going to follow us around for the rest of the semester as we apply this to sample analyses. So they're a little bit more important than the other ones here, which we probably will never speak about again in our lifetimes. Well, hopefully me. Well, no, I'll be doing it again next semester, right? So I'm doomed to talk about this stuff every 6 months forever till the end of time. Okay, so let's see. Let me get let me just remember these numbers: 55 and 8 and 10-year-old and 10. The 55, 6, and 48. Okay. Okay, just draw this normal distribution. We said, matter of fact, it's kind of a giveaway, right? Because we said right off the bat. Okay, where is it? There it is. Said it was approximately normal, right? So approximately normal might look roughly like that. The mean was 55 inches. The standard deviation, sigma, for the population was 6 inches, right? Okay, and we're interested in what's the probability that a 10-year-old is, that we randomly select from this population is less than, they say 48 inches. Okay, so we're looking at the proportion of children in this population that are less than 48 inches. In other words, this percentage of the normal distribution of the population as it stands. Okay, so how do I calculate? Well, now I need, in order to figure out what this area is, I need to know what the z-score is. So the z-score is going to be equal to the value I'm interested in, x, minus the mean over the standard deviation. That's the number of standard deviations away from the mean. Okay, that's equal to 48 minus 55 over 6. That's 7 over 6. Did I get that right? I didn't mess up any numbers there. Okay, so 7 over 6, that's a negative number, by the way, right? 48 minus 55 is going to be 7 divided by 6 is equal to 1.16666. I'm going to call that 1.167. Negative, right, exactly. Okay, is equal to negative 1.167. Or if I only have 2 digits to play with, negative 1.17. Okay, so now I have to go to my z-table, which is going to give me the standard normal distribution, so I can figure out what area that negative 1.67 represents. I'm going to open that up. Oops, where's Z? Z. Okay. Here's my z-table. So a z-score of negative 1.17 is negative 1.1, and the last digit is the number of columns across, right? 1, 2, 3, 4, 5, 6, 7. Negative 1.10, 1, 2, 3, 4, 5, 6, 7. So that's 12.1% or 0.1210. Oops, didn't mean to do that. Okay, is equal to negative 0.11210. Now I'm flying without a net here. So if I'm getting this wrong, or if I transfer the numbers incorrectly, you guys that are online, especially where you can have a little bit easier way to look this stuff up, will be able to, perhaps will be able to correct me. Okay, so it looks like 12% of the children are under 48 inches. So our chance of selecting one randomly that's under 48 inches is about 12%. If I had asked the converse of this question, which is, what's the probability you would have picked someone that was more than 48 inches tall? It would have been the area to the right of that, which would have been 78 inches, 88 inches, right? Which would have been this area in here instead. In fact, most likely, if I run through the form, probably the next question here is going to ask that, right? That's usually the way I'm going with this stuff. What's the probability that a randomly chosen 10-year-old is between 60 and 65 inches? Ooh, I made it a little bit more complicated. Okay, let's take a look at that. Matter of fact, I'll draw it again. Okay. And I'm going through this a little bit more than the others because, again, this is kind of a lead-in to some of the material we're going to move on to. 55 inches. Standard deviation is 6 inches. So I've said, what's the probability being between 60 inches and 65 inches? 60 inches and 65. Was it 65 or 66? 65. Good. Okay, so I want to know what percentage of these 10-year-olds are in this range right here, right? So I'm complicated. Both of these are on the positive side of the mean, right? They're above the mean. But both of them have a z-score, right? Each one of these things has a z-score. So I'm going to calculate both z-scores. The z-score is equal to 60 minus 55 over 6, right? Which is 5 over 6, okay, which is equal to, okay, which is equal to 0.833. Okay, I was just called 0.83. Okay, and the other one, z, is equal to, I did 65 minus 55 over 6, which is equal to 10 over 6. And that comes out to 1.67, right? Am I right about that? 4 over 6. Right? 1.67. Okay, so now I have two z-scores here, right? Both positive. So now, in order to figure out what the area is in here, one of the techniques I can use is I can say, well, the area from here down is, I don't know, let's call it 90%. The area from here down is, let's call it 70%. So that would mean the area in here has to be 20%, the difference between the two of them, right? Because that's all that's left. This is all of the area below. This is all the area below that. So if I cut this 70% away from that 90%, I'm left with 20%. So now I'm going to do it for real. I'm going to actually do the calculation. Okay, so my first z-score is going to be for 65, 1.67, positive 1.67. In other words, the area to the left of that z-score. 1.1, 1.67, 1.60, 1, 2, 3, 4, 5, 6, 7. So it's 0.9525. So this area is 0.9525, right? About 95%. And 0.83, 0.080123 is 79.67, 7967. So 9525 minus 7967. Okay, bring that over there, and that's 8, right? 8, 4, that's 11, 5, 4, carry that over here, 14, 5. I'll show you old school way of doing this, right? It's about 15.5%. I don't know what they teach now in schools, right? New math. There's probably a whole new technique for doing it. You see me crossing all these numbers off and carrying numbers. Those of us have a few gray hairs. That's the way we learned how to do this. But that area between there is about 15.5%. That means that the chances of my picking a random student that's within that range of numbers is 15%. Okay, how does that work? Is that okay? Does that make sense to you guys? You guys comfortable with that? Yes. Okay, good. At least somebody said yes. How about Christine, who answered the question? Who asked the question? Did that help, Christine? Okay, we're going to be going over this again too. So, if there's still some remnant of uncertainty, we're going to beat that to death. Let me just make sure. Don't know what that is, but let me make it go away. Okay, the next couple of problems. The height requirement for oh, this is an interesting one. The height requirement for the Batman ride at Six Flags Magic Mountain is 54 inches. I don't know is there a Batman ride?
Yeah.
There is? Okay. Okay, good. We kind of made that up. I thought there was, but it's somewhere in the back of my head, I thought there was one. And I wonder what the real height, 54 inches, I guess. Probably even less than that, right? Like 48. Yeah. So, but anyways, we picked 54 inches. What percentage of 10-year-olds cannot go on, are going to be crying because they can't go on this ride, right? When I was a kid, there was a thing at Coney Island called the steeplechase. And they had these horses, right, that would run on these metal tracks. And it was a steeplechase. And you could go on with two people. So I went on with my big brother one time, so on the steeplechase. But they had something called a parachute jump. And it's still there. Hasn't been used in 40 years or so, 40 or 50 years, 50 years most likely, right? And I always wanted to go on a parachute jump. Now you sat on a bench, right? So it was more than one person, usually 2 or 4 people or something like that. And they pulled you up, and it was on a cable. So the cable went through the middle of the parachute. So when they let you go, it was literally a parachute drop, but it couldn't go anywhere because it was tethered to the cable. So it just came straight down, and then you'd bounce when you got to the bottom. So I always wanted to go on to that, and it closed before I reached the legal height for that. So this problem has a special place in my heart here. So let's see what percentage of 10-year-olds are not going to be at that height. Okay. So, and this is actually pretty simple, isn't it? Okay, and 55 standard deviation is equal to, I'm sorry, what was this? 54 inches, okay. 55 inches was the mean, 6 inches was standard deviation. So the percentage of 10-year-olds that couldn't go on this ride are going to be whatever this Z-score represents. Z is equal to 54 minus 55 over 6 is equal to 1/6, which is, what is 1/6? 1/6, 1 divided by 6 is 0.17 for our purposes because we only have 2 decimal places to work with. So we would go to our Z table. We would look that up wherever it went. Where did the Z table go? There it is. 0.16. 0. Am I on the right side? Don't worry, it should be as negative 0.16, right? 0.010, 1, 2, 3, 4, 5, 6 would be 53.64. 43. Yeah, 0.16. Oh, 17. Was it 16? Yeah, 17. I rounded. Yeah, it should be 17. So 43.25% would be the percentage of 10-year-olds that wouldn't make it onto the ride. Now, there is one other thing, one other problem that I could have asked about this, and that would have been, what if I had asked you, what height would the 10%, what would be the height at which I would have 10% of the tallest students, right? The mean is 55. The standard deviation is 6. So what height would this be that I could say that 10% of the students in this population are this height or taller? How would I figure that out? Well, I would need to, I know the area I want. In this case, it's going to be the area to the left, which is then 90%. I know I want to know what X represents 90%. What height represents 90% of the population is smaller than that, right? So I know the area that I want, but I just don't know what X is. Well, I'm not going to know what X is, but I sure can calculate what Z is for that value. So I can say Z is equal to X minus 55, the mean, over the standard deviation, which is 6, right? Well, now what Z do I put in here? If I know what Z is, I only have one unknown left, right? So let's go to our Z table. Okay, here's our Z table. And what we're looking for now is the area that represents 90% of the area in this distribution, right? The Z-score represents. So instead of looking at the Z-scores of finding an area, I'm going to find an area 90%. 89. Looks like the closest thing to 90% is going to be here, which is 1.28. Okay, so 1.28 is the closest that I'm going to get here. So Z for this value is 1.28, positive 1.28. So 1.28 is equal to X minus 55 over 6. So get the 6 out of the way and multiply both sides times 6, right? So now I got 6 times 1.28 is equal to X minus 55. So I bring the 55 by the other side, so it's 55 minus 55 plus 6 times 1.28, right, turns into a positive sign, is equal to the value I'm interested in. So what is 6 times 1.28? Okay, clear. I'm going to clear everything here. 6 times 1.28 is 7.68. And I'm going to add my 55 to that right here. So the height at which 10% of the students are taller than is 62.67 inches, 62.68 inches. So I was able to do the opposite, use the table to find an area, find the Z-score for that represents a proportion of the population instead. So a little bit backwards from what we did there. Okay, so good. So Venn diagrams, I'm not going to beat this to death because hopefully you'll never see these again in your life. So I think that's where we stand. So most of you guys did really well on the test. I'm really impressed. Nobody really tanked on the test. So that's a good thing. Go back, continue to do the homeworks. Go back and redo the homeworks until you get, I love it when I see people that go back there, do the homework 5 times, and each time they do it, it's a little bit higher score. Because I know that means they didn't cheat and look at the answers. They actually went back and tried them again until they got another one right, and they tried it 5 times and finally figured all the questions out. It does my heart good to see that stuff. So go back there and take advantage of the fact that you can improve the grade on your homework. And maybe if you didn't do quite as well as you wanted on the test, those extra points on the homework are going to help you out later on in the semester, later on towards the end of the semester. Okay, and please also consider working on the city program thing, so that I don't have to hound you the last week of the semester. But please do it. Because it's gonna be a lot easier if you do it a little at a time than if you're up the night before. Whatever. What's our last day of class like? July 28th. What's that? 27th, July 27th. So you're not up on July 26th, at midnight, with 6 hours of reading to do. Okay. Okay. Yeah, there's a place in the assignments where you can click on it. I think, let me go there right now just to make sure that I'm not lying to you. My version of Blackboard looks a bit different than yours, so it may not be exactly the same. But I think if you go into assignments, you should see a city program right here. And if you click on that, it should give you a place where you can attach a file. You can upload it here. So you should see that on your version. It's back a little bit. I push these into the order that's most recent, like the assignment 3 that I posted is up here now, and 2 and 1, and then at the bottom was the first thing that came up, which was this city program certificate. Okay, click. Okay, good. All right. So now let's see what we're going to do. We're going to move on to now. I just want to talk about for a second. We started talking about central limit theorem. We did that a little experiment with the sample of 100 numbers, and we learned that when you take a population, right, and you then take samples from that population, and you make a new distribution, and that new distribution is the distribution of sample means from that population. Here's the population, and here's the sample means for repeated samples of size, I'm going to say 25, let's say. Let's made that number up. One of the things that we know about this is that both of them are going to have the same mean, mu, and the average mean for repeated samples. The more samples we take, it's like losing in Vegas. The more you play, the more likely you are to give the money back, right? So the odds are going to come out in the long run. So the mean for all those sample means is probably going to emulate the mean for the population. But the main difference here is that the standard deviation for the population, which I'm going to call that, and the standard deviation for these repeated samples means from a size 25 samples, which I'm going to call standard error, right? It's really a standard deviation. Sample means, but we're going to call it standard error. That the relationship between them is that the standard error is equal to the standard deviation divided by the square root of the sample size, right? So the variability, the width here for sample of size 25 is really 1/5 the width of this population. So I really should have drawn it more like that, I guess, right? So this is the relationship that we're interested in. That the way that these samples are going to be distributed, that's what we're really interested in. Because by doing that exercise, we've learned something about the way samples compare to their populations that they're drawn from. Very important to us. Okay, and the reason why that's important is because we will never know what mu is. 99% of the time, we will never know what the population mean is. If I ask you what's the average blood sugar level for patients 80 to 90 years old in New York City nursing homes, we're not going to go and sample every nursing home patient in that range. However, we might take a sample of 100, go around to 10 different nursing homes, selected, stratified, and go around and pick them out and pick 10 random patients at each one, or maybe just randomly select patients from some larger population somewhere. And we might actually take a sample of size 100, right? That might conceivably happen, right? And we're going to know what the mean of that sample that we took is. We're going to know what X bar is for our one sample. Well, before we were talking about taking samples like this over and over and over and over again to build a new distribution. But we only did that because we wanted to understand what the relationship was between the population and the sample. So I did get, from this sample, I got a result which said the mean is equal to 80, argument's sake, right? And what else did I get from this sample? I got a standard deviation for this sample. Well, the sample standard deviation, just like the mean is going to, just like X bar is going to approximate the mean, population mean, the standard deviation of sample is going to approximate the standard deviation sigma, standard deviation of the population, right? So if you take a big sample like 100, you're in pretty good shape. You're getting pretty close to I don't know about the mean, but you're getting a pretty good window on the standard deviation. For the first few problems that we're going to wind up doing tonight when we come back, we're going to do the lecture. I'm going to play the lecture. Then we're going to come back and do a bunch of problems and do some exercises, right? For the first few problems, I'm going to make up a situation where you know the mean that you got, but you also know the population standard deviation. Where might that happen? Well, let's say you were doing a study on a smaller group that had a very large study done on it, the Framingham study with 40,000 doctors, something like that, right? And maybe it measured the average number of cigarettes that they smoked or something like that. It was a heart disease survey. And let's say that you said to yourself, okay, well, that 40 sample size of 40,000, I'm going to assume that I know the standard deviation or the number of cigarettes smoked for all doctors, right? Just because it's such a large sample. So there are situations where you almost might make that assumption that you know the population standard deviation, even though you don't really, but you really pretty much on a practical basis do. Also, if it's a really large sample, I might say sample size of 100. I'm going to assume that this is true and just assume that the standard deviation and that I got for my sample is the same as the population standard deviation. Both cases might come up, right? But what does this mean? This means now that you're guessing at the mean, but you know what the distribution is. You know how it's distributed. So if that's true, you know the variability here for a sample of size 100. Let's say that the standard deviation, or sigma, right? You could look at it either way, comes out to be, I don't know, let's say 20, right? You know now that the standard error of repeated samples is going to be, standard error is going to be equal to sigma over the square root of the sample size, which is 20 over the square root of 100, which is equal to 2. So if you know what sigma is, you know how these samples of size 100 are going to be distributed. And you know that each standard deviation away from the mean is going to be a value of 2. So you can say to yourself, let me draw let me make believe that I could draw this distribution. And this is the distribution of all possible outcomes. And I say to myself, well, in the middle is going to be this 80. Let's say I assume for a minute that this is right. Then 2 standard deviations away to the left and to the right is going to be 76 and 84. And that I can pretty much depend, because I know the standard deviation of the population, I can pretty much depend that if this is really the mean for the population, for this sample and the population, that this is the way repeated samples are going to be distributed. They're going to be 2 standard deviations within this value, close to this value. Now, the problem is that you don't know whether that's the middle or not. That could be down here. Could have been this sample. 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 Right? All you know is that you would expect there's a 95% chance that most of these samples would be within this range of them. In fact, what you can say is that you can say that you have 95% certainty, right? That the true mean, which would be the average of all these possible means, same thing as the average of all these possible means, the true mean is within 2 standard errors of 80. So in other words, 95% confidence interval is 76 to 84. You're 95% sure that the true mean is between 76 and 84 because you know the standard error is 2. And you know that roughly 2 standard errors below and above this is going to be 95% of possible outcomes. So what did you do here? You predicted based on your sample and knowing the standard deviation. You predicted that you're 95% sure that the true mean, this guy right here, which is really what you're interested in, is between these 2 numbers. Think about that. Before, you only knew that, gee, I think 80 is somewhere near the real mean. Now, not only do you know that the real mean is likely to be between these 2 numbers, but you know the probability that you're going to be right about that. You've added that to this whole equation. Now you understand the likelihood that the true mean is between these 2 numbers. That's much more powerful now, isn't it? Before, you could only guess, hey, I think I'm close to the mean. Now you can say, I got these 2 numbers, and now I can quantify my level of certainty. Not only that, I can manipulate it as well. Now, if I wanted to, I could say, really, how many standard deviations apart is 95%? Not really 2, is it? Right? It was really 1.96. Right? We went over that, right? 1.96 and 2.58 would represent, 99%, half a percent here, half a percent there. The middle 99% would be 2.58, and the middle 90% was 5% here, 5% chance of being out there. What that was equal to 1.64, right? Well, I can now, if I wanted to, predict a level of confidence of 99%, right? And what would that confidence interval be? That confidence interval would be, instead of 2 or 1.96 times 2, it's going to be 2.58 times my standard error, right? Which is equal to 2.58 times 2, added and subtracted from my calculated mean, which was 80. And that's my 99% confidence interval. Is my 99% confidence interval narrower or wider than my 95% confidence interval?
Wider.
It's wider, right? This is a bigger number because we multiply by 2.58, it's added and subtracted, which makes sense. By having a wider confidence interval, we're more confident. Instead of being 95%, we're 95% sure, 99% sure that the true mean is between those two numbers. Okay, so if we're going to go to 90% confidence, it's going to be 1.64, which means it's going to be a narrow. We're willing to be less certain. We can give you a narrower range.
It's 1.64.
Yeah, 1.64. I can show that to you. If you look at the reason why we use those three numbers, because let's look at the normal distribution, right? Use the empirical formula, right? Right? We said -2 and +2 was 95. It's really not 2. It's 1.96. 1.9 and minus 1.96 to plus 1.96 leaves 2.5% out here and 2.5% out here. Now, if I want to go down to 0.5% here and 0.5% here, which means that the middle is 99%, you'd have to be at minus 2.58 and plus 2.58. Right? And if you were willing to be 5% here and 5% here, so the middle is 90%, right? Then you would be at 1.64 and minus 1.64, right? If I show you so I quickly show you. I really didn't intend on going this long on this part of this, but I think we need to see this anyway. And if I look here, let's say 2.58, let me use this end. Negative 2.58, negative 2.50, 2, 3, 4, 5, 6, 7, 8. There you are, right in there. That's 0.5%. That's 0.5% here, and a plus 2.5 is going to be 0.5% there. So in between there is 99% of the distribution. How about 1.96? Negative 1.0901, 2, 3, 4, 5, 6, and there's 2.5%. 2.5% on one side, 2.5% on the other side means 95% between, right? And 1.64, negative 1.60, 1, 2, 3, 4 is about 5% on each side, leaving 90% in between. So that's how we get to those numbers, okay, for finding the confidence interval. Now, confidence interval is important. I'll give you an example of why the confidence interval might be important, okay? One reason the confidence interval, oh, good, you guys down there, you are giving me the right answers on there. I appreciate it. Okay, let me just make sure I didn't miss a question here. Yeah. 2 standard would be 7. Yes, everybody, oh, good. Okay, good. Good work on there. Okay, so now I lost my train of thought now. Okay.
Why is the confidence interval important?
Yeah. Why is it important? Okay, so let's say that I took a sample of 100 Americans, right? And I took a sample of 200 Frenchmen, right? Now, let's say that I wind up and I find that the mean cholesterol for American men between certain ages and so on and so forth is 164. And the mean for Frenchmen, Americans, Frenchmen, is 155, right? Well, I can see that the Frenchmen are 155 and the Americans are 164. So my impression is that the average American whole population has a higher cholesterol than Frenchmen do. Problem here is that I don't know how certain I know that number. I don't have a handle to say it's a sample mean, but what's the probability that I got that high a number just by chance, right? That's where confidence interval comes in. If based on the standard error here, if I can say that the true mean for all Americans is between 160 and 168, and for Frenchmen is between 153 and 157, right? I'm 95% sure that the true means for Americans are between these two numbers, and I'm 95% sure that the true means for Frenchmen are between these two numbers. Both cases, I'm 95% confident, right? So notice they don't overlap. So that means even though they could be 160 and 157, they could be closer than I measured here. I'm 95% sure that they're different from one another. On the other hand, if for Americans it would have been, say, 158 to 172, and for Frenchmen it would have been 150 to 162, right? Well, these two overlap now. So I could be 95% sure, and Frenchmen could be 162, and Americans could be 158, and still be 95% sure. So who knows? Maybe it isn't true. I don't have the confidence to say that I'm 95% sure that 95% confident that they're really different. We're not going to use the confidence interval. We're going to use the confidence interval strictly to predict what our level of confidence is for the mean between two numbers. We're not going to use it to compare this way. We're going to use a different technique, which really is kind of like a similar thing, except where it constrains us to some rules that keep us from making some mistakes. We're going to calculate the number of standard errors apart that these two means are from one another. And we're going to call that, instead of the z-score, most of the time we're going to call that a t-score. The reason why we're going to call it a t-score is because we use z-scores when we know the population standard deviation. We use something called a t-score or t-distribution when we don't know the population standard deviation, and we have to depend on the standard deviation we calculate from our samples. So we're going to be looking, when we come back, we're going to start to look at applying this to calculate confidence intervals, and then deciding when we get away from the z-score and have to use that thing called the t-score. Okay, so you guys that are online, we're going to, let me go to Blackboard, show you where we are. I think I might have put up one of Professor Weicha's lectures. I think I'm starting to get my voice back finally. Yeah, I know. It was miserable cold. Let me tell you. Okay, let's see. I'm sure it'll give out by the end of the night, but at least it'll last that long anyway. Okay, let's see. Let me go over here to sessions and go in here and see where we are. Okay, so I think it's Levi's. Okay, so I'd appreciate it if you guys would play this at home. I'm gonna kill the live broadcast. Let's play this at home. I think, let me see how this is an hour and 5 minutes. So 6:30, 7:30. What do you say about 7:45? We come back again and we go live again, and I'll go over those examples that we're going to do for the online session. So you guys, goodbye for now, and I'll see you guys in a little while. What's that?
They don't have the lecture.
I'm sorry.
They don't have this link.
You're
about to show us.
This link over here? It's on. No, it's on session 6.
We don't have that. I don't see it either.
You don't see it? Oh, look, it's not available. Oh my goodness, I'm glad you mentioned that. Hang on a second. Okay, pull back the curtains again. Pay no attention to that man behind the curtains, right? Wizard of Oz. Oh, you're right. I can't believe I didn't make that available. Okay, good. I'm glad you mentioned that. Otherwise, these people will be staring at their screens over there and wonder, what the hell is this guy talking about? He screwed up again. That's what they're going to be thinking. Okay. Oh, we don't have that in capital letters. Okay, Christine. She's shouting. Christine's shouting at me. All right. Okay, good. That should be available now. It is available, right? Oh, no problem. That is available though, right? Guy, somebody online confirmed for me that you can see. You might have to reload the page. Okay, good. Yeah, I got somebody to confirm. Okay, see you guys at 7:45. Okay.